Now moving on to Ly and Lz. So here there are two ways. Till wherever the node is not broken, there we can choose to ignore it. But again, it has some funda that defining Lx and Ly that you need to understand first. So going back in a paint, so when we have a portal frame and there is a member over here. Now, if we are talking about Ly first, and if this is a minor axis in this direction, the one that we are defining, so with a moment connection, which is rare in a minor direction, but in case if it's there, then we can define this particular length as a Ly length. And same way on top, if another moment connection is coming, then this will be another Ly. So if this is a 2 meter and another 2 meter over here, then for both the parts my Ly will remain 2. In similar fashion, if we are providing a brace, something like this, and it's a shear connection at the intermediate junction, again the Ly and Ly in both the part will remain 2. But what if there is no brace and only a shear connected member is provided? Then in a minor direction for this particular columns, we do not get any stiffness in that direction. Means if the load will be coming, then there won't be any member or anything that will try to restrain it at intermediate point. In shear connection, this entire column will move in application of a load direction. So when there is no brace and there's a normal shear connection, then this particular Ly, instead of providing an individual one, will be having an entire 4 meter as our Ly. I hope you understand my point. So that was about Ly. Now let's discuss about Lz. So again, taking a similar portal, I am having a fixity at bottom. Similar way, it was fixed at bottom here, just to make a stable frame. Right. So coming back to our next Lz. So to make you understand better, if we are seeing this particular column from top, then the arrangement will be somewhat like this. So if we take particular this axis, so along about this particular axis, it's my I section's major axis. So this is my ZZ axis. That's a major direction axis. And if I take an axis from center of my I section, then about this, my axis for this Y section is minor axis. So I'll say direction will be YY. So in this particular arrangement, my Z, the major axis, it's connected with a moment frames. So here again, if this is an individual 2 meter, then I'll be considering my Lz as 2 meter for top portion, and in a bottom portion again that Lz will be 2. Right. Here, since it's a moment connection with brace, without brace, it does not make any sense, since a moment connection is a kind of a rigid connection which provides stiffness to my member. So I'll say that my length will be broken in that case. Now let's understand a 3D image for a better understanding of the same concept. If I'll say that this is my major axis, so the columns are placed like this, and I have a moment connection in this line, and I have a minor on a longitudinal side, I have a members not exactly at the intersection of a moment connection, but somewhat above and below of that thing. So if I say that my moment connection frame is at 3 meter, and on top again I am having member at 3 meter, and this beams, they are coming at every 2 meter. So 2 meter, 2 meter and 2 meter, and at somewhere along the length, I am saying that there is a bracing connected to all these members. So even though these are a shear connected members, but somewhere at backside we are having a vertical brace connecting all these beams. So when I have to assign Ly and Lz for this particular column, my Lz will be this 3 meter, and on top again, because this both are the moment connection, so my top will be another 3 meter. So both the members, so the entire member will have Lz as 3. Okay, and if we talk about Ly, so in a minor axis we are having bracing at every 2 meter, so my Ly for an entire length will be 2 meter. So even for this particular junction, I'll say my Ly is 2 meter. So this is how we generally define our Ly and Lz. So let's go in a Staad and see how we assign that. So if we take initial first columns, so let me just define Ly and Lz. My member is coming at 2 meter, that's a first moment connection frame, and on top another 2 meter. So the entire column will have Lz as 2 meter. So this particular frame is 2 meter and this particular length is 2 meter. So my Lz will be 2 for this particular frame. So I'll say Lz. I'll be selecting a beam cursor and I'll assign for all the columns as 2 meter. Now let's talk about minor axis. So when we see that even though we are having a beam at 1.5 meter, so will I break Ly as 1.5 meter for this length? No, I cannot. As I explained you earlier, since there is no brace, so whenever the force is coming, this entire frame or this particular column will move spite of the beam is there, as there is no brace or nor this connection is a rigid connection. So we can skip this length and we can move on to the next height. So that's another 2 meter. Now here we can say that this frame is rigid since that it is backed up by a vertical brace. So it will give us a sufficient stiffness so that it won't move, or the length of the entire column will break at this particular junction. And in similar fashion on top we are having the next beam with a brace type arrangement at 2 meter at top. So the Ly for all these beams will be again 2 meter. So for whatever columns I have defined Ly, for a similar columns I'll have Ly as 2 as well. So this was about the concept of defining a effective length of a member. I hope you understood that. Now there is another practice that is going on, that certain times we can avoid this kz and ky, and we can simply multiply this factor to that particular direction of length. So if I don't assign kz that I have applied for all the columns in z direction, if I choose not to provide this parameter, then what I'll do is that for Lz, instead of providing 2, what I can do is that I can multiply this 2 over here. So Lz will be 2 for Lz will be 4 for all these columns. So that's a cantilever behavior in z direction. So 2L, that is the length that I am providing over here. In similar fashion, my ky, that's a minor axis, due to brace, I am having ky as 1. So I can choose to ignore this, I cannot provide this parameter, and I can multiply this Ly2 by 1 or whatever that ky factor is, and I can provide this particular length, modified length over here. So that is another practice which is famous in industry. So either way you can provide based on your suitable choices, though I prefer to provide ky kz and ly lz independently, even though both are related. Moving on to our next parameter, that is main and T main. Now main and T main are nothing but allowable slenderness limit for a compression members, that's a main, and T main is the allowable slenderness limit for our tension member. Now by default values will be 180 for a compression, so that's a main, and T main we are having a by default limit is at 400. Now certain times we want to use the default values, that's 180 and 400. So in main we can provide a value 0 instead of any number to it. So by default it will take a Staad by default values. And if you don't want to check your member for slenderness, then what you can do, instead of providing 0, you can provide any negative number over here. That can be -1, -100, anything, but it has to be negative. So when you provide main and T main as -1 or any negative value to it, so the Staad, what it will do is that it will skip this particular check. So my Staad will not check the member for its slenderness. Now what is the slenderness limit for our members? So as per the IS code, we are the code table 3 defines various slenderness limit for our particular members. So 180, that's the minimum value that you can see. Now that is for a compressive member that is resulting from dead load and imposed load. And for a tension member which has a reversal effect with a wind and seismic, it has a limit of 180. Similar way, for a tension member that's a pure tension member, the T main, since it's a tension, the limit is 400. So based on this particular table, you can define your main and T main. So let's just go and define what I'll do, since I'm comfortable with what Staad is taking. So I'll take main and I'll assign the value 0. So it will take a by default value. In similar way, I'll assign 0 for a T main as well, or you can keep the default value, that's 180, 400 based on your conditions. And so far I am okay with the default values, so I have considered 0, 0. Or you can do is that you can keep 200, that's a value for compression, and 300 for a tension member. So these are the two values that I have considered for main and T main. Moving on to a next parameter, that's a track. So what track does is that it controls the level of details which Staad provides in its result tab. So when you say 0, it will give you a few liner detail of each member. If it's a member 15, that's a beam member, then it will check what is the capacity and with what ratio it is passing. So with a minimum detail, it will give you your final output. But as and when you go with 1 and 2, the detail description will increase. So when you say 2, every check will be provided in detail in Staad output. So generally when we want to check like what Staad is doing and what are the checks that has been performed, we generally keep track as 2 so that maximum detail can be available. But again, this is based on the requirement. You can choose, if you don't want a lengthy report from Staad, you can keep the value 0. Or if you want, or if a client specific data is that they want to check individual check, then you can provide a 2 as a track. So let's provide it in our Staad file. I'll go in define parameter, and at bottom we are having this track. So I'll say 2 after current and add, and I'll say assign to view. So next we have ratio. Now we know that Staad runs on after analysis, it gives us a ratio, that's a utilization ratio, that with what margin my structural member is passing or failing. So generally by default the ratio value is 1. So when it's 1, you can say that the structure is marginally passing or it's just passing. Beyond that, or even at certain cases, one is also considered as a failure mode. So if you want to restrict your member sizes, as like if I want to restrict that beyond 0.75 or zero point 0.8, show that the members are failing based on your individual requirement, then what you can do is that you can change this ratio. So when you say that zero point 0.8 instead of 1, then whatever member sizes which are passing with a ratio more than zero point 0.8 will show as a failure, even though it's passing with Staad or with checks. But what you are doing is that you are restricting that limit. So above zero point 0.8, it will show all the members with a unity ratio which are exceeding that value will show it as failure. So let's just define that. Instead, you can go in parameter and define parameter. You select ratio and I'll say I want member beyond 0.9 shown as fail. So I'll say add and it will be assigned to view. So our major parameters are done over here. So to finish it off, we go into command tab and we define check code. Now check code is like we are telling Staad that parameter definition is done and you can proceed ahead with a design. So when we say check code, so for an entire structure which are part of this check code will get designed based on whatever the load that we have assigned under loading tab and parameters that we have assigned under design tab. Apart from that, we can use takeoff. So what does this takeoff command does is that for whatever the member size that we have used, it will give us the MTO, that is material takeoff, or the estimated tonnage of a entire structure that we have modeled. So we'll say assign to view and we are good to go. Now there are few optional parameters that I am going to tell you about, which are not applicable in all the files, but at least you should be knowing about those. So there is another command, that's seismic. So in seismic parameter, we are having two options. Either we go with 0, so that it will not take care of the earthquake loads by default. Means whatever is there in a section 12, the provision for a seismic detailing will not be part of this particular Staad. But if you go with 1, then the Staad will take care of the earthquake design loads and whatever there is there in section 12 of IS 800. So after seismic, we have a next parameters, that is IMM. In this, by default, value is 0, and what this 0 signifies that all members are beam members, that is by default. Now, as per the section 12, you have to classify all the members as beam, column and bracing members, since alone Staad cannot identify these members. So when we are considering X brace, we have to consider those as a bracing members. So for those you have to mention parameter 2. For all the column members, you have to define column member as 1. So this IM for column members will be 1 and 0 for all the beam members. Now SSY and SSZ. So these are the factors, that is nothing but response reduction factor R. So based on a brace frame, that can be either ordinary concentrically braced frame or a special concentrically braced frame and eccentrically braced frame. Based on this classification, along X direction, we can provide this R factor, and in Z direction, where we are having our moment connection, so there we can provide either a ordinary moment frame, that's a response reduction value 4, and a special moment frame which has a value of 5. So based on this particular table, we can define SSY and SSZ. So that was all about the steel parameters for IS 800. Once we are done, we can just simply run our file and see our results. So we can move on to the concrete parameters after this. So once our analysis is done, you can go in a post-processing mode and we can check the utility ratios over here.